Hi, this is a quick demonstration of a sequence effect based scheduling algorithm. So let me explain a little bit what's going on here. So imagine that you were tasked with scheduling a whole bunch of events across an entire year. So in this case, this is 200 events. So think of these events could be like performing arts events or sporting events. Or something like that. 200 events across an entire year, and then you can put them just about at any date. And each date you have maybe several different locations you could put them. And then also you have to put them into bundles. Bundle them together because you're going to sell these bundles individually. So customers are going to go and see maybe 4 or 5 or 6 shows all together. You sell them as a bundle. Think of these as like a season subscription package or something like that for performing arts events. So what this algorithm then is doing is trying to figure out what the right schedule would be if you were trying to optimize some sort of psychological effects. In fact, we have 4 effects that this considers. Peak effect, end effect, trend effect, and spread effect. And what these 4 effects do is they attempt to maximize, again, this psychological effect that actually has been sort of shown to exist in events like this, sort of these subscriptions where customers see things over time. So what is the peak effect? The peak effect is the utility of the event of the highest event within the bundle. Right? The end effect is the utility of the last event in the bundle. The trend effect is the linear slope of the line that goes, kind of goes through all of the points of the bundle. And then the spread effect is actually the number of days from the peak event to the last event. So this is what's called sort of spreading. So if I have several good events, like 2 really good events, I want to spread those out over time. So what's going on here? So we have actually 2 different solutions, a current solution and a best solution. The current solution is, well, first of all, this algorithm just kind of comes up and creates just creates a random solution. It's right here. It's called the original solution. We can calculate the objective, 164.18. Okay, that's great. It looks something like this. And then what the algorithm does is it goes through and it just takes a couple of these events, 2 or 3, maybe 4 events, and unschedules them and then randomly schedules them again somewhere else and then reconsiders the objective. And if the objective is better, then it keeps that. If it's not better, then sometimes it keeps it. Sometimes it doesn't. In fact, early on, this we're at about 400,000 iterations. This is going to run about 4 million iterations. Every single iteration is going to just take away 2 or 3 of these events and reschedule them. And early on in this algorithm, it's going to accept worse solutions quite a lot. So right here, we're like 82% of the time it's going to accept a worse solution, which means that if I reschedule these 2 or 3 events in a different place and my objective is actually worse, I might keep it. In fact, I probably will keep it earlier on. So what happens is the current solution just sort of jumps all around. That's what's going on. So remember, each one of these lines is a bundle. Each one of these dots is an event. Here's the days of the year, and then we have this event utility. In this case, we're considering event utility is distributed in a specific way. The fact it's an exponential distribution, which means that there's just a handful of really good events, and then most of them are kind of low, kind of right around here around I think the mean was 50 or something like that, so right along that. So that's what you can expect. So right now it's just this big spaghetti mix. Down here we have the best solution, which just says, okay, every time you see a solution better than the last best one you've found, keep it. Right? So we can see right now the best objective is 224. Started at 164, and it's just kind of fumbling around 200. So we're going to pause this for a minute and then see what it looks like in another million iterations or so. Well, remember, we're going to run at about 4 million iterations. It won't take too long, but let's just pause it so you don't have to sit here and watch it all. All right, we just passed 1 million iterations. So now we're at 229, still hovering around 200, and we're only about 70% probability of accepting worse solutions. So this type of algorithm is called a simulated annealing algorithm. It's been around for a while. The idea, at least, of just altering a solution just a small amount, and it's a meta-heuristic. Meta-heuristics are used when regular optimization solutions won't work because for one reason or other, simply because the problem is too complex to fix into a regular objective. And so that's the case here. We have sort of complex objective statement that has all kinds of weird things going on here. And so this type of solution algorithm does a pretty good job at solving it. All right, so let's take another break, and we'll be back in just a minute. All right, we just passed 2 million iterations, and we're now at 270 of our best objective, and we're kind of floating around 260 for our current objective. You can see that they're starting to become a bit of a form now. We're not bouncing all around quite as much as we were before. We're only accepting more solutions about 33% of the time. So we're starting to get a form for what a good solution should look like, and that's what we're after. We want to see sort of graphically what this a good solution looks like to learn from that. So a couple things about these different effects: the peak effect, end effect, trend effect, and spread effect. What do they do? So the peak effect, remember, that just means it's the highest utility event for each bundle. So what it does, in our algorithm at least, is it tries to separate all the really good events across different bundles, sort of share the wealth across different events. So sort of maximize the good events across all the different events. The end effect, of course, tries to maximize the end. We can start to see that already. It's trying to say, well, the last event should be really high, so we can see that that's happening in these best solutions. Trend effect, again, is the slope of the line. So we see some of these that are sort of jetting straight up. That's a pretty high slope, right? A pretty steep slope. It also sort of maximizes, makes sure that we're kind of going low to high all the time. We always kind of see this upward trend effect. The last one, the spread effect. So what does the spread effect do? Well, this one's a little bit weird. The spread effect, remember, is just the number of days from the peak event to the last event. The number of days from the peak event to the last event. So to maximize the end effect, we actually want the peak to be the end. That would maximize it. But to maximize the spread effect, we want the peak to be the first event. And we see a couple of these already happening. This is actually a peak event for this bundle. It's not like a super high, but for that specific bundle, that is the highest utility event, and it's the first event, right? And it also makes that we're going to see in a minute, really long bundles, right? That kind of lapse over the entire time period. All right, so we'll come back in a few minutes more, see what's going on. All right, we've just passed 3 million iterations, and our objective is up to 313 now, which is great, and we're sort of floating around 311, 12. And you can see that probability of accepting more solutions is much slower. So we're not moving a whole lot anymore. It looks like we have a pretty good idea of what the profile will look like. We're going to actually get just a slightly better answer. We still have like 1 million iterations. The last 1 million iterations is just really fine-tuning how to get like sort of the really best answer. But at this point, we can pretty much talk about what the best solution looks like. So we can see then that we end up with kind of 2 different profiles. One is this really long profile, right, where we have a peak event at the very beginning, and then we immediately go down, and then we have sort of this upward trend, very slight but upward trend, right? So that maximizes the spread effect. We can say that's the spread effect making those really long solutions, and we end up with a peak real early on, right? So that's one type of profile. The other profile is this profile where we have sort of these really high utility events, right, that have a real steep slope, jump out from the lowest utility events to the highest utility event. And it's hard to tell in here, but each of these bundles actually have exactly the same number of events. So there's really 4 events in each of these bundles. So they're squished together as much as possible. And there's different constraints in here saying, look, the events have to be at least 20 days apart. They can't be any closer than that. So what does that do? Well, the trend effect then wants to make really short, condensed bundles, as short as possible, with a lot of variability in the events, meaning it wants a really super great event coupled with a really bad event. With a bad event at the very beginning, towards the beginning, and then a good event towards the end. As opposed to these spread effect bundles, which are all, this isn't that much better than the other ones in the middle, right? It's not a super duper good one. And all these other ones are all about the same utility, right? We just kind of put them in the right order, and we see that that's what we get. So this is pretty interesting that, we can start out with something that looks like this, just sort of a big jungly mess. With this algorithm, we can figure out what the right type of profile should be, and we come up with these 2 different profiles that should be considered if we want to maximize these effects. One final thing, these 4 effects that we have here are all equally weighted in this algorithm, meaning that they're all given the same amount of weight in the objective statement. And we find out that it turns out that the peak effect and the end effect seem to be, and even the trend effect, seem to be much easier to maximize than the spread effect. All right, so we actually can easily, especially with this type of distribution of events, we can more easily maximize these other ones. And in fact, we could think of a way to just maximize these three and leave these equal to nothing. And so there's no spread effect, but maximize these other ones. I would just put all the peak effects, the peak bundles into the end, and we would maximize these three pretty easily. But if we were to do that, each of these would only have 100, which means the max I could get in the peak is 100, the max I could get in end is 100, and the max in the trend I could get 100. So the best solution I could get is only 300, and we're at 315 already, and we ended about 316 or something. So that's great. It means that I can actually come up with a better solution than what I could just sort of think of on my own with this algorithm. So that's about it. Again, the solution ends up looking pretty close to this when we're done. Thanks for watching.